the same things that we have already been doing. We're talking about integrals still. We have dealt with integrals, so this isn't new. We're still practicing them. We know an integral just means an antiderivative. Most of the time when we've seen them, we've had numbers here that we plugged in. If I don't give you numbers, that means we're going to get something in terms of x, and that's when we have the plus c on the end. So it's just doing an antiderivative with a plus c on the end and not actually evaluating it. So difference, a definite integral, we call it a definite integral if you have that a and b, your starting and stopping point. And when you work those, you will get a number answer because you're going to plug those into your antiderivative and subtract them. An indefinite integral does not have any limits. So we don't have any numbers to plug in, so we will get a function. We're going to get some kind of expression that's still in terms of x. So let's just practice. If I ask you to do the integral of 10x to the fourth minus 2 secant squared x dx, I'm just asking for the antiderivative. So the antiderivative of 10x to the fourth minus the antiderivative of 2 secant squared x. What has a derivative of secant squared? Tangent does. So it's just a 2 tangent x. But what else do I need? Plus c. We didn't have to have the plus c if we had numbers to plug in, because we talked about how when you subtract them, those c's cancel. But if I'm not actually plugging in anything, I have to keep that c. Let's take a look at this one. So if I asked you to evaluate this antiderivative, that's a little less obvious, isn't it? You know, if I just have a sine or a cosine, I can do the antiderivative, but can I do the antiderivative of a quotient? No. So let's see, can I rewrite this in? So this is a cosine over sine squared. So what if I separated those signs? Do you guys agree that this is the same as cosine over sine squared? What is cosine over sine? What is 1 over sine? Okay, it's still a product, but do I know of anything that has a derivative of cosecant theta, cotangent theta? The derivative of cosecant is negative cosecant cotangent. So the antiderivative of this would be negative cosecant theta. So I didn't do a product rule in reverse. This only works because the derivative of cosecant is those two things multiplied together. And then what else do we need? All right. This one. You guys do this one. Just integral practice. This is a definite one. You're gonna. So the antiderivative of x cubed minus antiderivative of 6x from 0 to 3. So if we plug in the 3, minus, put in 0, you just get 0. And we get negative 27 over 4. All right. Next one. It starts out not looking so bad. Antiderivative of 2x cubed minus antiderivative of 6x. Okay, but here's where it's a little dicey. I can't just bring this x squared up to the top. We have a 3 times 1 over x squared plus 1. Didn't you have this on your homework last night? That's, yeah, that was tangent inverse had a derivative of that. So those were the inverse trig functions. I didn't make you memorize their derivatives. For doing antiderivatives involving those, it would be, you know, class problems or homework problems, not test or quiz, because I didn't make you memorize them. But that is tangent inverse. And then we're going to go from 0 to 2. So if I put in a 2, 2 to the 4th divided by 2 is 8 minus 12. Okay, I don't know tangent inverse of 2. That's just asking me where does tangent equal 2. But tangent inverse of 0, that's saying when is tangent equal to 0? And that is 0. So this whole thing turns into a 0. So we get -4 plus 3 tangent inverse of 2. And you could put it in a calculator and get a decimal, but I'm content leaving it in terms of tangent inverse. One more. What would we have to do on this one? First, we have to divide. So 2t squared divided by t squared is 2. Plus t squared square root of t divided by t squared. So the t squareds drop, and we have a square root of t, or I could write that as t to the 1/2 minus t to the -2. So antiderivative of 2 would be 2t. Antiderivative of t to the 1/2. So if you add 1, that's 3/2, so reciprocal in front, so that's 2/3. T to the -2, if you add 1, that's -1, so you just need a plus in front. We put in 9, we get 18. The square root of 9, so 3 cubed is 27 times 2/3. 18. So it would be 32 and 4/9. You can tell me what that is as a decimal. I don't have that. Only 32.4 repeating. So that's just more of the same. A couple of them involve some tricks maybe we haven't done before. But the main idea is the same. Any questions so far? So let's talk about some places where these antiderivatives might be used. Could you get it? Sometimes you'll be asked to find net change. A net change is just the overall change from the beginning to end, so it's just an antiderivative. Okay, so an integral is the same thing as calculating net change. We see this in several different areas, we know rates of change happen all over the place. So if you were talking about the volume of water in a reservoir, the derivative would be the rate the water is flowing into. So then if you integrated that, it would be the net change. How much did the water level change? Okay, so a positive would say the water level went up this much, a negative would show the water level went down. If we looked at a chemical reaction, okay, so in chemistry. So a rate of change is how the rate of reaction is occurring. So the antiderivative would go backwards, take away that rate, so it's going to tell you the overall change in concentration from the beginning to end in that reaction. If you were looking at mass, okay, the derivative of that can give you the linear density. So if you do the antiderivative, it's telling you the overall mass between 2 points in time. We've talked about populations a lot. So a derivative can tell you the rate of change in a population. So an antiderivative would give you the net change. How much did our population increase or decrease by? So a derivative is a rate of change. An antiderivative goes backwards and tells you the overall amount of change. We've seen marginal cost is a derivative of cost, and we use that one a lot. If I did the antiderivative, it would tell me the actual amount the cost changed from beginning to end. So not the rate at which it was changing, but the overall, this is how the cost changed from producing 0 items to producing 50 items. We know if we have position, the derivative is velocity. So if you do the antiderivative, you're back to position. So it's a change in position from one point to another. So we've spent all year talking about derivatives and rates of change. You have to be able to think backwards now. What happens if I go backwards from that rate? We've kind of mentioned this one yesterday. There is a difference between if this is a velocity function. This would indicate that our velocity was positive, negative, and positive, right? Now there is a difference in asking you for displacement versus distance traveled. Okay, so if I am standing at the edge of my desk and I walk to the edge of this table and then back, my displacement is how far I am from where I started. And how far am I from where I started? 0, because I'm back at the same spot. But does that mean I didn't travel at all? No, my distance traveled is the whole way there and the whole way back, right? So distance is like the absolute value of those things. You have to add them together. If I want displacement, how far am I from where I started? That's when you add the forward and subtract the backwards. Does that make sense? So we can kind of be asked to find different things on some of these, and we have to pay close attention there. So let's look at a problem. We have a particle moving along the line. So the velocity at time t is given by this equation. I want to find displacement and distance. So displacement is just asking how far are you from your starting position. Okay, so if we're at velocity, then we are wanting to go backwards and get position. So we're just going to integrate from where to where? 1 to 4. Okay, we want the antiderivative of our velocity. And when we're doing this displacement, we don't have to do anything special because we want to add the positives and subtract the negatives. And an integral just does that for you. So we're just integrating this. So we would have the antiderivative of t squared minus the antiderivative of t minus the antiderivative of 6. I'm doing that from 1 to 4. So if I plug in my 4, so what did you guys get? You guys agree? What does that mean? Why is it negative? So this was in meters. All this means is your displacement, the particle, moved back 16.5 meters. Okay, that doesn't mean that's all it moved, but it ended 16.5 meters behind where it started. That's displacement. Now B, I want the distance. Distance is the absolute value. Okay, whether I'm moving forward or backwards, I am traveling a distance, so we need the absolute value of that. So think about how we do absolute values. We have to figure out what makes this equal 0. Okay. So set this to 0 and we get 3 and negative 2. Would both of those be relevant here? No, because we're only talking about between 1 and 4. So that means we're going to break this up. We're going to do from 1 to 3, and then we'll do from 3 to 4. Okay, if you put in something between 1 and 3, even if you put it in 1 itself, is this a positive or a negative? Negative. So the absolute value does the opposite. Can I just distribute a negative through all of that? Make it negative t squared plus t plus 6. But if you're between 3 and 4, even if you just plug in a 4, you get a positive answer. So the absolute value does nothing. Okay, essentially what this is telling us is from 1 to 3 seconds we were moving backwards, and then from 3 to 4 we went forwards. So now we integrate. We get negative 1/3 t cubed. This 1/2 t squared plus 6t. Let's see what we 2 over 6. Or that's approximately 10.17 meters. So even though you ended behind where you started, this is giving us our overall. That doesn't make sense with our first answer. Did we plug something in wrong on the last one? Because this should be bigger. The overall distance we traveled should be bigger than. I wrote +6 when I wrote this down. And that should be a -6. Do you guys see how I caught that mistake? Because your overall distance, if you went forward and backwards, that should be more than just your net change. So let's see what happens if we fix that. 9/2. That sounds better. Positive or negative?
I don't remember. I remember that's what I got originally, and I thought that I messed up. So
No, I think it should be a negative. So it moved back 4.5 feet. So it ended 4.5 feet behind where it started. Overall, though, it's moved a total of 10.17 because it went forward and backwards. All right, sounds good. Sorry about that mistake, guys. Let's try a book problem. So grab a textbook to share. All right. So this one, example 7, gives us a figure. And it says it shows the power consumption in the city of San Francisco for a day in September. The P, the power is measured in megawatts. T, the time is measured in hours from midnight. I want to estimate the total energy used. Okay. So cover up the answer. Don't look at their answer down here. How am I going to use this graph? So this is telling how much energy is used at any given point in time. If I want the total amount of energy that's used, what do we have to do? So you have some. The total amount of energy used, that's just the area under this curve, isn't it? Okay, but I don't even have an equation for that, so I can't calculate it exactly, can I? So we had them on the last test. How did we estimate areas under a curve? Let's even be less precise than that because we don't have the equation. Before we did the limits, we just did like the rectangles and add them up, right? So we can do, I don't know, how many rectangles do you want to do? We went from 0 to 24. So what if we just did 12 rectangles? So we could do a left-hand sum, a right-hand sum, or a midpoint sum. What would be the most accurate? Okay. What's the width of all these rectangles going to be? I'm going to use the midpoint rule with n equals 12. So all of these have a width of 2. So we know we take it times 2. And we need to be adding 12 numbers together. Okay, so to do that, we're going to use this graph. So the first one would go from 0 to 2. But if you're using the midpoint, where in that interval are you looking? So the rectangle will go from 0 to 2, but we're going to estimate it based off the midpoint, so we're going to look at 1. So we're basically finding the y value at 1. So when the x is 1, what would you estimate that y value to be? 450. And then we go up by 2. So next we're going to do When the x is 3, what would you estimate that y value? And then when my x is 5, it's definitely lower than 450, isn't it? 425. Then when we're at 7, 625. Maybe you overshot it a little bit, but not too bad. And then when my x is 9, 800. When my x is 11, okay. When we're at 13, still there pretty close to the 850, isn't it? 15, 850-ish again. At 17, at 19, at 21,
Like a 670.
and 23.
550.
So now we just calculate it. 2 times all of this stuff added together. I think my last one was really sloppy. That's 550. Kind of looks like a 580. And this was estimating the energy, so that would be megawatts. If you look down at their solution, were we close? The book estimated it at 15,840, so we weren't too far off from their estimate. Okay. You okay with this? Then this is the end of this section. I'm going to go ahead and give you problems. We will have a work day tomorrow, but you've got time to start now. Alright, so problem number 1. It's asking you to verify by differentiation, because that's not something we could have done the derivative of. So they're asking, they told you what the answer was. And they said, okay, the antiderivative of this is that. But this is something we could take the derivative of. So they're saying, take this derivative and see if it works. So, derivative. For this, you have to do a quotient rule. Okay, so low, the bottom, is everybody paying attention? Because I'm not going over it again. So low, the bottom is x. D high. So square root is like a 1/2. Exponent comes down, so you get a -1/2. Inside stays the same. Subtract 1 from the power. Times derivative of the inside. Will be a 2x. So that's low d high. Minus high. D low. Because the derivative of the bottom is just 1. Over low squared. And then we have this plus c, but what's the derivative of a constant? 0. So that's going to go away. Alright, this appears pretty ugly at the moment. X times -1/2 times 2x that would be a negative x squared. 1 plus x squared to the negative 1/2. That would just put a square root on the bottom of this. Okay. Then we have minus a negative, so plus square root of 1 plus x squared. And this whole thing is over x squared. We don't want a fraction in a fraction, so the easiest way to get rid of that is to say, alright, I'm going to multiply everything by the square root of 1 plus x squared. So if we do so, negative x squared over that square root times the square root, so those drop and you just have negative x squared. Plus, the square root of 1 plus x squared times the square root of 1 plus x squared would drop the radical. On the bottom we have x squared, square root of 1 plus x squared. On the top, negative x squared and positive x squared cancel.